Good evening, everybody. Chris F.E. Jackson here. Let's just adjust my microphone here. Now, people have been mentioning Sir Patrick Moore recently, and I did a video well over a year ago about can you speak Venusian? And just to give everybody a heads up before I do this, because this video, Can You Speak Venusian is available as a video, I think, on YouTube, but the book is free to download, and the link to that book is here. So if you go to this, just type in Can You Speak Venusian? And you can read this book online here. And if you click on it, I guess it will give you the index on it. And I think on this one, there is a section called Independent Thinkers. Then section 1, right there, the independent thinkers looking at the world. And he talks about the history of the Flat Earth Society. There's Mr. Bradbury there, God bless him, with his model. It's a very, very excellent read, this one, as well as good as the videos, but this book, with the first chapter, he celebrates the fact that there are people out there that do think differently to the mainstream science. And if anything, I think that Patrick Moore was a realist. He knew a lot more than he was letting on. He was very clever, and he had such a sustained and long career. Obviously, the Sky at Night was the longest. I think it still holds the record for the longest television broadcast program series in the world, and that happens to be on the BBC. And I think with Sir Patrick Moore, he probably had a lot of license to actually say what he wanted on that show, and he was probably left to his own devices because he was such a character and an institution really within the BBC and with the British public that he was held in with austere, and his enthusiasm and his knowledge and his celebrity status, if I dare say that, because he was on all these sort of primetime TV shows as a guest, and he was be seen as a little bit eccentric, but he was trusted, I guess. But behind the scenes, he sort of quite subtly and clandestinely, if I may say, actually was putting out messages there. And it's only just in the last few years that I really thought, my word, this guy was actually doing something. He's actually trying to tell us something or make us look up and perhaps take a look. And some of the things he says is over the years has been quite, that's a bit strange. But nevertheless, one aspect I'm going to look at tonight was just touch on briefly is a chap called Halton Arp. Now, Halton Arp was an astronomer and quite a long and distinguished career. Now, in a nutshell, what happened was his theories regarding galaxies and looking up there at these certain bodies in space, and his deductions, and he had his own theories for quasars and consequently redshift, and he proved in a way or proved statistically time and time again that the quasars were actually responsible for generating galaxies, and the string of quasars and the way they were actually together and actually formed tails between it and well, like an ejection, which caused energy. And even he said, I don't know what happens. It's almost it gives up its energy as it slows down, and so therefore it creates mass and it slows down and it emits light and so on and so on. So the quasars themselves, in a nutshell, I'm just rambling on a bit now, but the quasars in a nutshell, what he was saying was that where you had different colors, they were different, not distance, but different lengths of time that they'd been there. So as a quasar effectively cooled down or gave up its material, it changed in color, whereas the whole basis of redshift is the fact that these are supposed to be a lot further away. But he proved time and time again that the quasars were in the same vicinity as each other, when you talk in astronomical terms, it wasn't light years in difference. So the whole concept of what they say the universe is and how large it is based on something quite different to what Halton Arp had suggested. And like I said, he proved it time and time again. He struggled to get things published into Natural Science because they wouldn't publish it, and he lost all his observatory time. And he ended up working for a place in Germany, and one of these students who he thought was the next up and coming astronomer that was going to come out with all the new concepts, and he thought he was going to surpass everything in which he did. And I'm talking about Halton Arp still. And this poor young chap was ostracized by every academic institution going in terms of astronomy. And he ended up just writing for a magazine or something. So perhaps some sort of amateur astronomical association or something. I feel ashamed because I can't remember his name. But there you go. It just goes to show if you are that sort of person, when you come up with something and they just won't make it public knowledge. But anyway, that's the link for Patrick Moore and Can You Speak Venusian? Now, can you imagine, right, back in the day, Sir Patrick Moore, I won't do an imitation of him, but Sir Patrick Moore probably had license to actually pick and choose what he wanted on the program, because he would obviously tell the producers, "Oh, yeah, this time I want to run this, I want to look at that," and they'll say, "Yeah, okay, yeah, whatever, Sir Patrick, yes, we can help you with that." Or, if he said, "I want to get this sort of interesting chap on, this guy called Halton Arp, and he's an astronomer and he deals with quasars," and I'll say, "Oh, okay, Patrick, what was that name again?" Halton Arp. And he says, "Oh, Halton Arp, yeah, we'll see if we can get hold of him." And yeah, he said, "I'd much like to get him on the show," and he did that. And this is after Halton Arp had lost all his time at the observatories, but Patrick Moore had him on his program. Now, can you believe it? It's the sky at night, and he's there talking about what he believes in quasars. Now, I'm going to play the video, and you can actually watch Halton Arp's longer videos on YouTube, where he details in very, very good data and findings, and correlates that to other galaxies, and he proves it time and time again. And bless him, he gives, I mean, he's passed away now, but he does methodically go through it, and he has such a lovely manner about it as well. Now, somebody of any lesser character would have probably just been ranting and raving about it, but he never did, being such a professional, and he looked such a sweet man as well. He looked as if he had a really lovely temperament, and one that could easily be ridden over, I guess, without too much problem. And there you have it. I guess probably anybody with a slightly different temperament may have banged the drums a bit more, but that's no discredit to Halton Arp, by the way. So I shall play the like I said, Sir Patrick Moore had him on his Sky at night, and this is the video I'm going to play. So I'll just pop that up now, and it's the Sky at night, and I shall let you see what Sir Patrick Moore says. Now, this is 20 minutes long, by the way, so I might stop it and just point something out, but I shall let it play. So I hope you enjoy this as much as I did. And I've just given you a bit of background information as to who this chap is, Halton Arp. Look him up. I've actually bought one of his books called... oh, actually, while I'm here, let's pull that up. So this one here is... it's arriving Monday. I meant to do this. It's a catalogue of discordant redshifts by Halton Arp. Now, the other book he has is Seen Red. And I think it's this one here. Let's get that into shot, can I? I don't think this was available, this one. Let me just click on this a minute. Seen Red. Oh, sorry about this. I'll just say add to basket. Basket subtotal. It did say to me that that's the picture of him there, by the way. And he was in cahoots with a chap called Hilton Ratcliffe as well, and I'm not sure what happened to him. But anyway, I shall go back to There. So let's go back to here, and like I say, I shall play the. I've lost the video. No, here it is. There we are. Okay, so I shall play this, and I hope you enjoyed as much as I did. So he said there, redshift and controversy. It's controversial because his findings were different to the norm. And let's face it, if we had to take Halton Arps and his scientific approach to the astronomical aspects that he looked at was to be true, and if everybody accepted it, this would mean the ending of the Big Bang. Though it's a theory at the moment, it would undermine the theory of relativity and everything that's gone before, and it would just throw out every scientific experiment that's going on, or had gone on in the past and now and for the future. So they'd have to rewrite and redo everything. So what better to do than just discount him and just carry on as normal, right? Okay. I think that pretty much sums it up.
Good evening. And first of all, in response to numerous inquiries, that very brilliant star-like object in the western sky after sunset is indeed the planet Venus. But this evening, I want to go way beyond our solar system. We think we know a great deal about the universe, but do we? First of all, I'm going to give you a very brief, quite conventional account, and then we'll have a longer, harder look. So here goes convention. The Earth is a planet going around the Sun at a distance of 93 million miles. The Sun is a perfectly ordinary star, one of 100,000 million stars in the Milky Way making up our galaxy, which of course is by no means the only one. Far away, so remote that their light takes millions of years to reach us, we have other galaxies. They are the Andromeda Spiral, more than 2 million light years away, and even bigger than our own galaxy. And that's a member of our local group. Another member of the local group is the Large Cloud of Magellan, where the supernova blazed out quite recently. But that's only a start. Look at this picture. Here we have the Virgo cluster of galaxies, and most of the smudges in that picture are not stars, but whole galaxies, each containing perhaps 100,000 million stars, and around about 50 million light years away. And
so just to put things into perspective here, how do we know that they're looking at the macro and not the micro? They say millions of light years away. I don't know that. I mean, my last video I put out with the phenomenology, you may know the icon is a picture of space and stars. I made that myself, by the way. I mean, it's easy. It looks quite good, but you know. Anyway, I'm sort of going off the track here. Let's carry on.
that again is only the start. What about the quasars? The quasars, look at that little tiny dot there on the end of the arrow. That is a quasar, and according to conventional theory, it's superluminous, perhaps as luminous as 1,000 whole galaxies put together, and is more than 10,000 million light years away, and is receding at more than 90% of the velocity of light. Now, how do we tell that? And the answer is by using the spectroscope and the well-known Doppler effect. Remember, a spectroscope splits up light. And when you look at the spectrum of a star, or a galaxy, you see a rainbow background crossed by dark lines, each one of which is due to some particular element or group of elements. Now, if the light source is moving away, its light appears slightly too red. And that means that all the spectral lines are shifted over to the long wave or red end of the spectrum. That is the red shift, and it is absolutely vital because all our distance measures in the far universe depend upon it. Let's go back again to that quasar. Now, how do we know it is so remote and so luminous? Because of its red shift. The greater the red shift, the greater the distance, and the greater the velocity of recession. That's the conventional theory. But that depends upon the red shifts being pure Doppler effects. Now, just suppose there's some other cause of the redshift superimposed on the Doppler effect. And if that is so, if the redshifts are not pure Dopplers, then all our distance measures may be wrong.
Now, see, bear in mind, he is open to the fact that there may be some other explanation. This is his time on the BBC, which is going out worldwide to whomever, and this is going out to mainstream audiences who have interest in, professional and amateur astronomers. And for him to sit there and say that, I think this is absolutely all credit to Sir Patrick Moore. And, God bless him. I mean, you can see that he is a free thinking person, not an independent thinker, but a free thinking, allowing the debate to continue question science and what they pervade, and have all aspects to be looked at, which is fair, is what we should be doing today with anything, which we should be allowed to do and speak and debate regarding and look at the evidence. And so, again, I'm starting to waffle on, but I can't stress the point more than enough, and this is what this gentleman did.
And one astronomer who believes that and has observational evidence to back it up is Dr. Halton Arp, formerly of the Mount Wilson Observatory and now of the Munich Institute. Dr. Arp, we're delighted to have you with us. If you're right, then the effects upon all our thinking are going to be pretty profound.
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much.
Well, first of all, then, will you give us the observational evidence that you have that the redshifts are not pure Doppler effects or something else superimposed on it?
Fundamentally, the only way you can tell the distance in the universe is to see an object associated with another object whose distance you know. So that if you see objects which are clustered together or are interacting together, you know that they're at the same distance. And if you find that their redshifts are much different, then you know that the redshift can't be a measure of the distance. Now, an example of this we see in this very pretty spiral galaxy with 3 quasars on the edge of it. The quasars have enormously high redshift, and the spiral galaxy has a low redshift. These quasars are so close to the galaxy that they are statistically or probably associated. We see other examples of this. For example, here are 3 other quasars associated very, very close to a galaxy. Now, in addition to these close associations, which are statistically probable, we see quasars actually linked to the galaxy. In this case, the quasar Markarian 205, just below the disturbed galaxy NGC 4319, has a very much higher redshift than the galaxy, which is only about 2,000 kilometers per second. The quasar has about 21,000 kilometers per second. The next example shows a quasar of very high redshift, 1.17, and it's connected by a luminous bridge into a disturbed galaxy with a jet that you can see here. The galaxy is, again, very much lower redshift, and the quasar is a high redshift. Now, not only do we have these quasars of very high redshift linked and associated with lower redshift galaxies, but also we have galaxies themselves of different redshift, which are clearly interacting but have much different redshift. This is a famous example of one of these. There are many like this known now. The central galaxy is a disturbed Seaford galaxy with a redshift of 8,000 kilometers per second, and the companion, which is linked to it, is 16,000 kilometers per second, much higher.
So what he's saying there is that the basis of what the difference in redshift is what they're saying it is. So he's saying that this one has 16, this one has 8, and to current science and thinking of the distance and the speed that the redshifts are differing is that this one should be further away. Oh, sorry, I'm pointing. You can't see what I'm pointing at. How silly of me. Anyway, this one here is redshifted different to this. So what they're saying is this one here isn't as far away as this one, or vice versa, whichever way around it was. But you can see here this spiral link between the two. And when he said earlier about the redshifts of the 3 quasars being redshifted around the central galaxy with a connection to it, this is what he's talking about. So they're all in different states of redshift. All 3 quasars with the galaxy are all different redshifted. And so according to the current science, that's the calculation of the distance and the speed, because as it's further away, it would take longer for the light to get to us through the space-time continuum, right? So it stretches the light, so it's shifting it to the red spectrum. And so, but he's saying, no, look at this. And he does mention it briefly. You can go back and listen. He says, statistically, it's been proven. He goes time and time and time again, where he makes these connections between the quasars and the galaxies and galaxy groups as well, which is very important. And he states that he doesn't know how these things give up its energy. It could be a slowdown in momentum, so it gives up its energy, and therefore it just connects. But I'm no expert. I've read his stuff. I've got another book coming to read. It once you get hold of this, it sort of I can't let it go. So here we go. It's great.
Now, are you sure these links are genuine? Could it be any kind of line of sight effect?
The only possibility is that there is an accidental projection of background objects. However, these objects fall so close that the probability is overwhelmingly that they are in fact associated. One of the objects we just saw, the chances was 1 in a million for an accidental association. Another object we just saw, the chances were 1 in 50,000. And there are many of these known.
In other words, there are too many of these cases to be explained away by line of sight effects or just coincidence.
That's right. Statistical investigations of complete samples have shown repeatedly that there are these significant associations. Moreover, they are characteristic patterns in these associations which are repeated from association to association.
Well, that means, in fact, that the redshifts are not pure Doppler effects, and they're simply not reliable as indicators of distance.
That's right. The only observational test of this assumption that we have shows that the assumption is not correct.
Well, quite apart from that, what about these bridges? How exactly are they formed, and are there any distortions between various systems?
I think a good example is this NGC 4319 object, where you can actually see the luminous connection going from the center of the galaxy to the quasar Markarian 205.
What about the significance of the bridges, then?
Well, I think the significance is very central here, because the bridge goes back exactly to the center of the galaxy. That implies that the material was ejected from the center, and since it's an active nucleus, this makes good sense. Also, we must remember that it's accepted, and it's been proven, that the galaxies eject radio material, and they eject them in equal and opposite directions, so that it's very well accepted and believed that, in fact, as we see here, for instance, an active galaxy nucleus ejects these clouds of radio material, and in this particular case, there is a quasar associated very nearby. In another example, we see this typical radio galaxy ejecting radio material in either direction, and along the line of the ejection is a compact radio source, which in fact turns out to be a quasar of very high redshift. So that, in fact, we know that galaxies eject material, and the only point is what is being ejected. Now, we can see here, I think, one of the most spectacular examples of ejection. This is a spiral galaxy called NGC 1097, and this colored picture shows the long, straight jets coming out from the center of this galaxy. In the next picture, which is a black and white, shows better the contrast in jets. You can actually see a faint fourth jet. Again, always the ejection and the opposite ejection, showing luminous ejection of material from this galaxy. But now in this particular galaxy, it's very interesting because there are also radio and X-ray observations. The radio observations are shown here now on the black and white photo. The radio observations are shown in yellow, and they show that the radio material also goes along the line of these ejection of these jets. Finally, the X-ray observations are shown in blue. There are clouds of X-ray material around the nucleus of the active galaxy, obviously ejected from the galaxy, and obviously ejected in the direction of these jets, which are shown here in this picture. But now the really very important and impressive point is that in many of these clouds of X-ray materials, there is a point of light which turns out to be a quasar of very high redshift. These are marked by the X's. And these quasars of high redshift, therefore, are linked to the ejection in this galaxy, because because the radio material, the optical material, and the X-ray material are all ejected with these quasars.
What about the remarkable galaxy Messier 82 in the Great Bear?
M82 is a very well-known galaxy. It's a very strong radio source. It's a very strong infrared source. It's very disturbed. It's been known for a long time to be ejecting material. You can see it here in the picture. And accidentally, it was discovered that there were 4 quasars very nearby. These 4 quasars are indicated by these open circles, and it's very easy to draw this ejection cone back to the center of the active galaxy, and at the base of the ejection cone you see this little radio cloud. And most important of all, again, if you look at the X-ray observations in this galaxy, you see that the X-ray material is also coming out in this direction of these quasars.
Well, if quasars are being shot out from active galaxies, there might even be some in our local group, which is quite a thought. But now, what about galaxies themselves? Are there cases of galaxies which appear quite clearly to be associated and yet have totally different redshifts?
There are a large number of cases now where galaxies of quite different redshifts are seen to be interacting together, showing that they're at the same distance despite the fact that they have much different redshifts.
There you go.
A famous example of this, a much discussed example, is Stephan's quintet. Here you see the redder galaxies in the upper part of the picture have large redshifts, 5,700, 6,700 kilometers per second. And the blue galaxy in the lower part of the picture has a low redshift, only 900 kilometers per second. And yet you can see the interaction tail of the low galaxy due to the low galaxy interacting with the higher redshift galaxies. Now, something else is very interesting about this picture, and that is that these kinds of interacting galaxies typically occur in the outskirts, in the regions around big dominant galaxies, SB galaxies like our own M31, that dominate a group. So if you look a little ways away from Stephan's quintet, you in fact see this type of SB galaxy. It's called NGC 7331, and it looks just very similar to M31. Around that galaxy, you see other companions, like Stephan's quintet, essentially the same redshift, 6,700 kilometers per second. They're obviously associated with 7331. It illustrates the kind of groups which make up space, which I think make up space, big dominant galaxies, and companions around them which have the slightly higher redshift and increasingly higher redshift, but are all located in the same region of space.
Again, you think there are too many of these to be put down to coincidence?
Yes, yes.
What about M31 and M81? They are 2 of our near spirals.
This follows the development of this investigation of groups of galaxies through to the most impressive point, I think. The M31 group and the M81 group are the 2 groups that we know the most about. The M31 group is our local group. We know all the companions in it. The M81 group is the next nearest group. We know all the companions there. This visual shows that the biggest galaxy in each group is the SB, M31, and M81. And now all the rest of the companions, which everyone has always accepted as being companions, have systematically higher redshift. The chance of 21 out of 21 companions being of accidentally all of higher redshift is only 1 in 2 million. But on the Doppler interpretation, we should have as many coming towards us as away from us, plus and minus. Clearly that's not the case, and clearly this is a point which is just inescapable. No future measures are going to change these redshifts, and we're not going to find any more companions, so we have to deal with this piece of evidence.
Well,
So what he's saying is that statistically, what he's saying is that if that was the case and it was down to the redshift and the way these things are rejecting, you would expect them to be coming either way. So if it's coming towards us, it would be in the blue shift. He's not seeing the blue shift, okay? Only redshift. So I guess that ties in ties in with the expansion of the universe, but these things have been created in space, right, as we speak, most probably, and it's not a dilemma he's got, but he's saying that we should expect to see something coming towards us, not just going away. And 21 out of 21, 1 in 2 million. He's got other statistics as well.
You're certainly painting an entirely new picture. How do astronomers in general view it?
I think that that there's a great commitment to the assumption that redshifts always mean velocity, and there's a great reluctance to give up this assumption because a lot of work has been based on it.
Everything.
And there is this reluctance to recognize evidence which contradicts this assumption. However, if it's true that the redshifts are not always indicative of velocity, and it's continued to be believed that it is, if this assumption is continued to be believed, then we reach a very critical point in the science of extragalactic astronomy. And this is so important that I think that everybody, every person then has to make up his own mind, exercise his own judgment on this matter, and therefore I think it's very important to discuss the facts of the matter as we have here.
I'm quite sure you're right there. Well, I'm no cosmologist, as you know. Anything beyond the orbit of Neptune is rather a long way out for me. But if you're right, and there is an extra redshift superimposed on the Doppler effect, what's the cause of this non-velocity redshift?
Well, the first point I have to make is that the observations show that the present assumptions are inadequate, so we have to have some other explanation. I think there are a number of explanations which are possible and which different people defend in a very spirited way. That's as it should be. My particular hypothesis, my working hypothesis, my explanation is that the matter which goes into making up these quasars and these higher redshift galaxies is young matter which has intrinsically high redshift, which is ejected from the galaxy and which decays and evolves as a function of time into more normal lower redshift galaxies.
Well, in general, it's generally thought that the high redshift galaxies are a long way away, and the high redshift quasars are the most distant, and therefore the most luminous. What you're saying is that instead of being the most luminous, the high redshift quasars are actually the least luminous.
That's the most exciting point for me. If the material out of which these newer quasars are formed has low mass, in the sense that the constituent particles, the electrons and the protons, have lower mass, then their redshift will be high. Now, there's a rigorous theory due to Fred Hoyle and Jean Narlikar that the mass of elementary particles, of the constituent particles, can evolve with time. My application of that to this situation is that it's the evolution with time of the mass of these particles which causes the initially high redshift to decay and become more normal.
So he mentioned Sir Fred Hoyle. That very interesting fact that the way he said that people defend this rigorously, whereas he is more open to rather have a discussion about it. He has his own hypothesis, but he doesn't defend his hypothesis. He puts it out to question, whereas other people's, so their agenda is different to his. His agenda is more genuine. But he mentions Sir Fred Hoyle there. Sir Fred Hoyle was not an advocate of the Big Bang. I think everybody knows that, or the Big Bang theory. I should repeat. So, in essence, how much more of a genuine scientist and astronomer does anybody want in someone like Halton Arp? They should all be like this gentleman in the future, shouldn't they, really? This is the type of person we want there, giving us a true and theoretical basis on and putting forwards their hypotheses for discussion. But no, they don't want to do that because they don't want to upset the apple cart. I shall play on. There's about another 3 minutes left on this, so very interesting what Sir Patrick Moore says at the end, but I shall not spoil it for you.
In current physics, though, is this kind of creation of matter a possibility?
In past years, it has not been a very respectable thing to talk about creation of matter. And that's a little puzzling, really, because it's had a long and honorable history. The brilliant physicist Paul Dirac, more than a generation ago, talked about the creation of matter. Hoyle and Bondi and Gold talked about the creation of matter in connection with the steady state theory. Andrei Sakharov in 1965 suggested the creation of seeds of galaxy creation this way. So it has an honorable history. However, just recently it's become much more respectable because of inflation theory. Inflation theory is the attempt of physicists to explain the expanding universe by means of fundamental physics, And in that process, they conceive of creation of matter. The technical term they use is fluctuations in the material vacuum. And essentially, you're looking at a piece of space, and the properties vary, and suddenly some material appears. Well, why not? My hunch is that the material appears where material previously exists in the center nuclei of galaxies, and that then this material flows out along the bridges or perhaps along the spiral arms. And this particular spiral galaxy we see here, we see that there is a disturbance in the top, in the arm at the top, and if we look in more closely, we find a very peculiar blue object associated with that spiral arm. And if we take the spectrum of that object, we find, amazingly, that it has a redshift a tenth the velocity of light, an enormous discrepancy. This reminds me of the remark that Sir James Jeans made more than a generation ago when he suggested that spiral galaxies perhaps were the place in our universe where matter was poured in from other universes.
Well, that's a kind of cyclic universe.
Wow.
Whether you're right or wrong remains to be seen, but it's a fascinating new picture, and of course it does stand or fall on the observational evidence. You presented a case, and now it's up to people to consider it and see what the evidence is. And I think we're going to have some very exciting developments in the near future. We're delighted to have you with us, and I hope you'll be back with us soon. So for the moment, from Dr. Arp and myself, good night.
We urge you not.
So, I don't know what this is. Let's go back to here. Let's bring that back up. Okay. So there you are. What he said at the end there was all the different observations can be hopefully talked about in the future. What happened? Nothing. And this was filmed in 1988. 31 years ago, and where are we now? Still with the Big Bang, the redshift, and the expansion of the universe. So people, there you go. I hope you enjoyed that as much as I did. That's the second time I've watched that. Thoroughly enjoyed it, and I'm looking forward to receiving my book. I meant to order that weeks ago, or some time ago, and but life and work gets in the way as usual. So thank you very much. Appreciate that, and yeah, I'll catch you all about it at some point. Okay, thanks for watching. Be safe, everyone. Goodbye.